Welcome to this online course on Introduction to Integer and Mixed Integer Linear Programming. This program is brought to you by the Institute of Computer Science at Forth in collaboration with TwinODIS. In this course, we will explore one of the most powerful and widely used optimization frameworks in modern decision-making, integer and mixed integer linear programming, often abbreviated as ILP and MILP. Throughout this course, we will build the mathematical foundations needed to model such problems correctly and solve them efficiently. Importantly, this is not just a theoretical course. You will learn how to implement models using Gurobi, a modern commercial solver, translate mathematical formulations into code, and interpret solver output in practice. By the end of the course, you will be able to A. Formulate real-world decision problems as MILP models. B. Understand how modern solvers actually work internally, including branch and bound, cutting planes, and relaxations. And C. Confidently implement and solve MILP models in Python. Let's begin. To begin with, the structure of this course follows a deliberate progression. We start with the foundations, what MILP is, how it differs from classical linear programming, and why integrality fundamentally changes problem complexity. We will explore typical business motivations and see where these models naturally arise in real use cases. Next, we move into the algorithmic backbone of modern MILP solvers. You will learn about LP relaxation, branch and bound, and cutting planes, not from a purely theoretical perspective, but from a practitioner's viewpoint. The goal is to understand what the solver is doing internally when you press optimize. After establishing this conceptual foundation, we shift to hands-on modeling in Gurobi. We will define variables, add constraints, specify objectives, run the optimizer, and interpret the results. Finally, we consolidate everything with a structured assignment problem that resembles a real-world industrial decision-making scenario. By the end, you will have a solid grasp of the core principles of MILP and be equipped to formulate and efficiently solve an MILP model for a real-world business problem. Let's start with the simplest class of optimization problems, those involving only continuous decision variables. In this setting, variables can take any real value within a specified interval. When both the objective function and all constraints are linear, we obtain a linear programming problem, or LP. LPs are mathematically well-behaved. Their feasible region forms a convex polyhedron, and the optimal solution, if it exists, lies at one of its extreme points. This convex structure is what makes LPs computationally tractable. Algorithms, such as the simplex method or interior point methods, exploit this structure efficiently. In practical industrial settings, LP models arise in blending problems, production planning, energy dispatch, and network flow optimization. Fractional solutions are often meaningful. For example, shipping 3.7 tons of material is acceptable. Modern solvers like Gurobi can solve extremely large LPs very quickly. However, many real decisions are not continuous. We often must decide whether to build something, assign someone, or activate a facility. That is where integer variables enter and where complexity increases dramatically. When decision variables are restricted to integer values, the nature of the optimization problem changes fundamentally. Even though the objective function and constraints remain linear, the feasible region is no longer a continuous convex set. Instead, it becomes a discrete collection of points. This loss of convexity is critical. Integer programming problems are, in general, NP-hard. That means computational effort can grow exponentially with problem size. Unlike LP, we cannot rely solely on geometric properties to find optimal solutions efficiently. In industry, integer variables appear whenever decisions are indivisible: number of machines installed, number of workers assigned, number of vehicles deployed. You cannot build half a warehouse or hire 0.3 of a technician. Because of this discreteness, solvers, such as Gurobi, must use advanced tree search techniques, systematically exploring candidate solutions while using clever bounding strategies to avoid full enumeration. Understanding the shift from convex optimization to combinatorial search is essential when designing practical MILP models. Most real-world optimization problems combine continuous and integer variables. This leads to mixed integer linear programming, or MILP. Consider a supply chain example. You might decide whether to open a warehouse. This is a binary variable. Once open, you decide how much product to ship through it. These are continuous flow variables. The binary decision changes the structure of the feasible region, while the continuous variables determine operational quantities. This combination makes MILP extraordinarily expressive. It allows us to model fixed costs, logical implications, capacity activation, minimum order quantities, and many other practical features that LP alone cannot represent. From a computational perspective, MILP solvers repeatedly solve LP relaxations inside a branch and bound framework. Each node in the search tree corresponds to a modified LP. So even though the overall problem is combinatorial, LP technology remains the engine inside the solver. This hybrid nature, combinatorial search powered by continuous optimization, is the core of modern MILP solving. Mixed integer linear programming, or MILP, is an optimization framework in which both the objective function and the constraints are linear, while the decision variables may include both continuous and integer variables, including the important special case of binary variables. The strength of MILP lies in its modeling flexibility. First, it enables the optimization of complex operational systems, where decisions are inherently discrete, such as assignment, selection, scheduling, or design problems. Second, it has proven to generate substantial efficiency gains and cost savings across a wide range of application domains, including logistics, transportation, finance, telecommunications, and network design. Third, and perhaps most importantly from a modeling perspective, MILP allows us to encode logical structure within linear models. Using integer and binary variables, we can represent implications, mutual exclusivity, conditional activation, and structural dependencies, effectively embedding elements of first-order logic into an optimization framework. This expressive power, however, comes at a cost. Introducing integrality significantly increases computational complexity compared to linear programming. To better understand this difference, we now turn to a direct comparison between LP and MILP. Before analyzing the differences, it is useful to recall the general process for addressing an optimization problem. We begin with a real-world decision challenge and translate it into a mathematical model. This involves specifying the objective function, defining the decision variables, and writing the constraints. Together, these elements define the feasible region of the problem. Once the model is constructed, a solver applies mathematical algorithms to search for and ideally find the optimal solution. At a high level, this process is identical for both LP and MILP. The difference lies not in the modeling of workflow, but in what happens inside the solver. Now, looking at the table, let us analyze these differences more carefully. First, variable types. In LP, all variables are continuous. This means the feasible region is a convex polyhedron. In MILP, some variables are integer or binary. This immediately destroys convexity and introduces combinatorial structure. Second, geometry of the feasible region. LP feasible regions are continuous and convex. This guarantees that local optimality implies global optimality. In contrast, MILP feasible regions consist of discrete points embedded within a polyhedron. The solver must identify which of these discrete points is optimal. Third, optimal solution. In LP, the optimal solution always lies at an extreme point or vertex of the feasible polyhedron. In ILP, the optimal solution must lie on one of the integer feasible points. In MILP, the optimal solution combines both aspects. Conceptually, The solver searches over discrete configurations, and for each configuration, solves a continuous optimization subproblem. Fourth, computational complexity. LP problems can be solved in polynomial time using well-established algorithms. MILPs are generally in NP hard. In practice, this means solve time can grow exponentially, in the worst case, as the number of integer variables increases. Finally, fifth, solution strategy. LP solvers exploit convexity by moving along edges of the feasible polyhedron using algorithms such as simplex or interior point methods. MILP solvers, on the other hand, rely on branch and bound and related methods. They repeatedly solve LP relaxations, partition the search space, compute bounds, and prune regions intelligently. Let us now look more carefully at when integrality is truly necessary in a model. The first and most obvious case is naturally indivisible quantities. If a variable represents the number of machines installed, trucks deployed, or employees assigned, fractional values simply do not make sense. You cannot operate 3.6 vehicles or hire 2.4 technicians. In such cases, integer variables are not optional. They are required to maintain realism. The second case involves binary variables, which can represent structural commitments. These decisions often trigger fixed costs or activate capacity constraints. Third, integrality becomes essential for expressing logical constraints. For example, if project A is selected, then project B must also be selected, or two alternatives may be mutually exclusive. These types of implications cannot be captured with continuous variables alone. Finally, integrality may be introduced to represent nonlinear functions. For example, a production process may have stepwise cost structures or minimum batch sizes. Let's now analyze further the case of binary variables. First, we have binary variables representing yes or no decisions, often referred to as go-no-go decisions. Examples include build a new plant or not, undertake a new marketing campaign or not, develop a product or not. These are pure binary choices. The decision variable can only take the value 0 or 1, and that single bit fundamentally determines whether a strategic action is implemented. This is one of the most common uses of integrality in practice. Second, binary variables are used to formulate multiple choice decisions. For example, among several possible investment strategies, we may be allowed to choose only one. This is modeled using binary variables together with a constraint that limits their sum to 1. In this case, integrality enforces exclusivity among alternatives. Third, binary variables are helpful for introducing variables with two distinct values, such as in batch processing environments. For instance, if equipment is used, it must produce exactly B units. If it is not used, production is 0. This creates a variable that effectively switches between two operational modes, off or fixed level production, and requires integrality to represent that discontinuity. Another important situation requiring integrality arises when modeling logical constraints that involve selecting elements from a set. In many optimization problems, decisions are not only about quantities, but about choosing specific elements from a predefined collection. For example, we may need to select certain projects from a portfolio, choose facilities from a candidate list, or determine which configurations are activated within a system. Binary variables allow us to associate each element of the set with a decision variable indicating whether it is selected. Once these binary variables are defined, logical rules can be enforced through linear constraints. We may require that exactly one element be chosen, that at most one be selected, or that some elements can only be activated together. The table presented here summarizes several typical logical relationships and how they can be translated into linear constraints. It illustrates how selection rules, dependencies, and exclusions can all be expressed using binary variables and simple algebraic formulations. What is important is that integrality allows a structured decision-making to be embedded directly into the optimization model. Rather than handling logic separately from optimization, Both are solved simultaneously within a single mathematical framework. Logical constraints can be converted into linear inequalities in a very systematic way, and the procedure follows a small set of repeatable steps. Start by eliminating implications. Any statement of the form if, then, is rewritten as a disjunction, so the logic is expressed using OR rather than an implication operator. Next, if negations are present in inconvenient places, push negations inward using De Morgan's rules. The goal is to end up with negations applied directly to individual Boolean terms, rather than to larger expressions. Once the expression is written using ANDs and ORs, and especially when more than two Boolean terms are involved, recursively distribute OR over AND. This step is essentially a normalization step. It rewrites the expression into a form where you have an AND of clauses, and each clause contains only ORs. Then, replace the Boolean variables with binary decision variables. This is the bridge from logic into optimization. Each Boolean becomes a 0 to 1 variable. Finally, translate the normalized logic into inequalities. Each clause that contains only OR operators becomes one linear inequality. And whenever you have an AND between clauses, that simply means you add additional inequalities, one per clause. As an example, here we illustrate how the logical constraint expressed as if product A is chosen, product B cannot be chosen, and product C must be chosen, can be translated into two linear inequalities, shown in equation 1. Disjunctive constraints arise when the feasible solution must satisfy one among several alternative sets of constraints. In logical terms, this corresponds to an OR condition between constraint systems. Here, without loss of generality, we assume two general linear constraints, as shown in equation 2. In order to model constraint feasibility, we first define a binary variable yi that selects which constraint is active. Then we apply the big M formulation and modify constraint I so that it is enforced when I equals 0 and relaxed when ui equals 1, as shown in equation 4. Note that the constant M must be sufficiently large to deactivate a constraint when needed, but not excessively large, since overly large values weaken the LP relaxation and may cause numerical instability. Finally, we combine the linear constraints introduced with a multiple choice constraint and get the finally set of linear constraints shown in equation 5. This formulation allows logical OR relationships between constraint systems to be represented within a linear mixed integer framework. We are now ready to talk about the last case where integrality arises. This is nonlinear functions representation. In particular, we are going to explore integration of fixed costs in the objective function. In other words, costs that are incurred only if an activity is performed. The modeling structure typically involves a binary activation variable, y, and a continuous activity variable, x. For example, assume x product units with a fixed cost k, that is the cost for setting up the equipment, and cost per unit c. In addition, production capacity is b units. We introduce a binary variable y that equals 0 when no units are produced and 1 otherwise, as defined in equation 6. Then, the contribution of x product units to cost is defined in equation 7 and the constraints in equation 8. These constraints imply that x equals 0 when the fixed cost is not incurred, that is when y equals 0. Note that the constraints themselves do not imply that y equals 0 if x equals 0. However, when x equals 0, the minimization will clearly select y equals 0, so that the fixed cost is not incurred. Finally, if y equals 1, then the added constraint becomes x less than b, which reflects the capacity limit on the production equipment. Another case of nonlinear functions representation is that of the piecewise linear functions. Assume a piecewise linear expansion cost curve, as shown in the figure. The total expansion x is decomposed into 3 segments, corresponding to the 3 linear pieces of the cost curve. Introduce continuous variables x1, x2, x3. Each variable represents the expansion within one segment of the piecewise linear cost curve. So any total expansion x can be written as in equation 9. Since each segment has its own capacity limit, we express the bounds as the constraints of equation 10. This means that the first segment can contribute at most 4 units of expansion, the second segment can contribute at most 6 units, and the third segment can contribute at most 5 units. The total expansion is constructed by allocating expansion across these 3 segments, respecting their individual upper bounds. We now continue the piecewise linear formulation by introducing binary variables. Define 2 binary variables, yy1, yy2, that indicate whether a segment has reached its upper bound. As stated in equation 11, each YYI equals 1 if the corresponding XI is at its upper bound and 0 otherwise. These binary variables allow us to enforce the sequential structure of the piecewise linear expansion. The cost function is then defined as shown in equation 12. The coefficients in that expression correspond directly to the slopes of the 3 linear segments in the cost curve. Next, the continuous variables and binary variables are linked through the constraints given in equation 13. Those constraints ensure the following structure. The first segment can be used up to its maximum length. The second segment can only be used if the first segment is fully utilized. The third segment can only be used if the second segment is fully utilized. The binary variables y1 and y2 take values in the set 0, 1, and they control the activation of the segments. We can generalize this formulation as shown in equation 14. For S segments with length Lj for segment j, the constraint shown there enforces that each segment j can only be used if the previous segment has been activated. This construction guarantees the correct sequential filling of the piecewise linear function. As a result, the nonlinear cost curve is modeled exactly using linear constraints combined with binary variables, while preserving the intended economic structure of the expansion problem. When the cost function is not naturally piecewise linear, we can still model it within a MILP framework by approximating it. The idea is to use piecewise linear representations to approximate general nonlinear functions. Instead of working directly with the smooth nonlinear curve, we replace it with several linear segments that approximate the original shape. We then formulate and solve a mixed integer linear program using that piecewise linear representation, following the same modeling approach described previously. The structure of the model remains linear. The nonlinearity is captured through the segmentation and, when needed, binary variables that enforce the correct activation pattern. Accuracy depends on how many points we use on the curve. By adding more points, meaning more linear pieces, we reduce the approximation error. In other words, increasing the number of segments improves the fidelity of the representation, but it also increases the size of the model. This creates a practical trade-off between solution accuracy and computational effort. In this way, even general nonlinear functions can be handled within a MILP framework through systematic piecewise linear approximation. So far, we have discussed modeling components in isolation: binary variables, logical constraints, piecewise linear representations. To make these ideas concrete, we now turn to practical use cases. The first use case concerns strategic investment decisions. Capital budgeting problems arise when a company must choose among competing investment opportunities under limited resources. Here, the goal is to maximize the total contribution obtained by selecting investments from a finite set of possibilities. These possibilities may include plant locations, equipment configurations, research and development projects, and similar strategic decisions. Partial investment is not allowed, which means that this is a go-no-go problem. Each investment is either fully selected or not selected at all, and the objective is to maximize the total contribution, defined as the sum of contribution coefficients times the decision variables. The model is subject to resource constraints. So for each resource, The total amount used across all selected investments must not exceed its availability. The decision variables are binary. Each variable equals 1 if the corresponding investment is selected and 0 otherwise. The table summarizes the notation. Xj represents the selection of investment. Cj is the contribution of investment. Aij is the amount of resource I used by investment. Bi is the availability of resource I. This formulation captures a fundamental discrete investment selection problem under limited resources. The same capital budgeting framework can incorporate logical considerations. For example, consider a contingency rule. If investment 1 is accepted, then investment 2 must also be accepted. The objective and resource constraints remain unchanged, and the logical dependency is enforced through an additional linear constraint, labeled as the contingency constraint. This constraint ensures that selecting investment 1 automatically forces the selection of investment 2. The structure remains linear, and the decision variables remain binary, as in the original formulation. Another logical structure is multiple choice. Suppose that only one of the first 4 investments can be accepted. The objective function and resource constraints remain the same as before. The logical restriction now is implemented by adding a constraint that the sum of the first 4 decision variables must be less than or equal to 1. This guarantees that at most, one of those 4 investments is selected. Again, the model remains linear, and the binary variables enforce the discrete selection, illustrating once more how logical conditions such as exclusivity are modeled using simple linear constraints. We now move from a strategic investment decisions to an operational planning problem. Warehouse management is about balancing 2 competing cost components: transportation costs and the operating costs of distribution centers. The objective is to minimize total cost. To do that, we must decide which warehouses should be open and how much product should be shipped from each warehouse to each customer. There are 2 fundamental requirements. First, the demand of every customer must be fully satisfied. Second, shipments can only originate from a warehouse if that warehouse is open. The objective function therefore includes 2 terms: the cost of shipping goods from warehouses to customers and the fixed operating cost of each open warehouse. The model introduces the following variables and parameters. Xij represents the quantity shipped from warehouse I to customer J. Yi indicates whether warehouse I is open. Fi is the fixed operating cost of warehouse I. Cij is the per unit cost of shipping from warehouse I to customer. Dj is the demand of customer J. This formulation captures both the location and allocation decisions within a single mixed integer linear program. We can now make the model more realistic by introducing capacity limitations. In practice, each warehouse has a limited throughput. Even if it is open, it cannot ship unlimited quantities. This is captured by adding a capacity parameter for each warehouse. The total quantity shipped from a warehouse must not exceed its capacity, and that restriction only applies if the warehouse is open. If the warehouse is closed, shipments must be 0. If it is open, shipments are limited by its capacity. This additional constraint strengthens the model and reflects real operational limits. The structure remains mixed integer linear, but the feasible region becomes more constrained and more realistic. We now move to a scheduling problem, and more specifically, to airline crew pairing. The objective here is to allocate crews to flight duties in a cost-efficient way, while ensuring that every required flight is operated. To understand the structure, we first introduce 2 key definitions. Legs are atomic flight segments. Each leg represents a single flight from one airport to another, and every leg must be flown exactly once. You can think of legs as the building blocks of the entire schedule. Routes, on the other hand, are feasible sequences of legs that a single crew can operate. A route forms a valid chain of flights that respects operational rules. In the figures, The individual legs appear as the small connections between cities, while the colored paths represent complete routes. Each route is mapped one-to-one to a crew. If a route is selected in the optimization model, exactly one crew is assigned to it. This scheduling problem therefore becomes a selection problem. We choose a set of routes so that every leg is covered exactly once and total cost is minimized. This structure naturally leads to a binary decision model, where each route is either selected or not selected. Building on the definitions of legs and routes, we now formalize the crew pairing problem. Each route corresponds to one potential crew assignment. Selecting a route means assigning exactly one crew to operate that sequence of legs. The objective is to minimize the total cost of the selected routes. Each route has an associated cost, reflecting crew wages, operational constraints, and possibly positioning costs. The key modeling requirement is coverage. Every flight leg, which we defined earlier as an atomic segment that must be flown exactly once, must be covered by exactly one selected route. To capture this, we use a binary parameter that indicates whether a particular leg is included in a given route. Then, for each leg, we enforce a constraint stating that the sum of all selected routes containing that leg must equal 1. This ensures two things simultaneously. First, every leg is operated. Second, no leg is assigned to more than one crew. The decision variables are binary. Each variable indicates whether a specific route is selected. The result is a classical set covering a structure, where routes are chosen so that all required legs are covered exactly once at minimum total cost. The formulation can be extended to reflect additional operational flexibility. In practice, a crew does not always operate every leg included in its assigned route. Sometimes a crew may travel as passengers on a flight in order to position themselves for a later leg that they will actually operate. This possibility changes the coverage logic slightly. Previously, we required that every leg be covered exactly once, meaning exactly one selected route must include that leg. With crew riding allowed, the constraint is relaxed. Each leg must still be covered, but it may now appear in more than one selected route. Operationally, this means that one crew operates the leg, while another crew might ride as passengers on the same flight. Mathematically, this modifies the coverage constraint from equality to an inequality. Instead of requiring the sum over selected routes to equal 1, we now require it to be greater than or equal to 1. The objective function remains unchanged. We still minimize total route cost. This extension preserves the binary structure of the model while better reflecting real-world crew scheduling practices. We now move to another classical routing problem, the traveling a salesman problem. Instead of assigning crews to predefined routes, we now construct a route directly. The setting is the following. Starting from a home city, the salesman must visit each of the remaining cities exactly once and then return home, while minimizing total travel costs. The decision variable indicates whether the salesman travels directly from city I to city J. The objective is to minimize the total cost of all selected travel arcs. Two structural requirements define the tour. First, each city must be entered exactly once. Second, each city must be exited exactly once. These two sets of constraints ensure that every city has exactly one incoming and one outgoing connection. However, these conditions alone are not sufficient. They may produce solutions that consist of multiple disconnected cycles, known as subtours. In such a case, the salesman would form several small loops instead of one single tour, visiting all cities. This is why additional constraints are required to eliminate subtours and enforce global connectivity. To ensure that the solution forms a single connected tour, additional constraints must be introduced. As discussed previously, the entry and exit conditions alone guarantee that each city has exactly one incoming and one outgoing arc. However, they do not prevent the formation of smaller disconnected cycles. To eliminate these subtours, we introduce auxiliary variables that represent the relative position of each city within the tour. These variables do not represent physical decisions. Instead, they serve as ordering variables that encode the sequence in which cities are visited. The subtour elimination constraints link these ordering variables with the routing decision variables. Their role is to enforce consistency. If travel occurs from city I to city J, then the position assigned to city J must follow the position assigned to city I. By imposing these linking conditions across all pairs of cities, the model prevents the creation of independent cycles. The result is a single connected tour that includes every city exactly once and returns to the starting point. With these constraints in place, the formulation fully captures the traveling salesman problem as a mixed integer linear program. Up to this point, we have formulated mixed integer linear programs. The natural next question is, how do we actually solve them? There is some bad theoretical news. First, integer programming is NP complete. Second, the LP relaxation can be arbitrarily far from the true integer optimum. And third, naive enumeration becomes infeasible very quickly because the search space grows exponentially with the number of discrete variables. However, the practical news is much better. In practice, there exist highly robust and efficient algorithms for solving MILPs. These methods are broadly classified into enumeration techniques, such as branch and bound cutting plane techniques, group theoretic techniques. Moreover, modern solvers combine methods from different categories, leading to very powerful hybrid approaches. In the MILP context, the standard relaxation is obtained by removing the integrality requirements and treating integer variables as continuous, while keeping all other constraints unchanged. At first glance, this may seem like a simplification that moves us away from the real problem. In fact, it does the opposite. It provides critical structural information that guides the search for the integer optimum. The key theoretical results explain why. First, feasibility. If the LP relaxation is infeasible, then the original MILP is also infeasible. This means we can detect impossibility early without exploring integer combinations. Second, bounds. For a maximization problem, the optimal value of the LP relaxation is an upper bound on the MILP optimum. For minimization, it is a lower bound. This is crucial. It allows us to evaluate how promising a region of the search space is without fully solving it in integer form. Third, optimality. If the LP relaxation happens to produce an integer feasible solution, then that solution is already optimal for the MILP. No further work is required. Together, these results show that the LP relaxation is not merely an approximation. It is a computational tool that provides feasibility information, quality bounds, and sometimes even the exact optimal solution. These properties are precisely what make branch and bound and other MILP algorithms possible. Now let's describe the branch and bound method, taking into consideration the properties of LP relaxation. Since the LP relaxation provides bounds and sometimes even integer solutions, the idea is to systematically explore the search space while using those bounds to avoid unnecessary work. Branch and bound is fundamentally a recursive divide and conquer strategy. We begin with the LP relaxation of the original MILP. If its solution is integer, we are done. If not, we select a fractional variable and split the problem into smaller subproblems by adding additional constraints. This is branching. Each branch defines a restricted feasible region. For every such a subproblem, we again solve its LP relaxation. This provides a bound on the best integer solution that could possibly exist within that region. If we already have a feasible integer solution, called the incumbent, we compare the bound of each branch to the incumbent value. A branch can be safely discarded or pruned if A, the LP relaxation is infeasible, B, its bound is worse than the incumbent, or C, the LP solution is already integer. In this way, the LP relaxation continuously guides the search, allowing us to eliminate large portions of the search space without explicitly enumerating all integer possibilities. The process continues until no unexplored branches remain. At that point, the incumbent is guaranteed to be optimal. To understand how branch and bound works in practice, consider the following integer linear program. We want to maximize z equals 5.5 x1 plus 2.1 x2, subject to the constraints minus x1 plus x2 less than or equal to 2, 8x1 plus 2x2 less than or equal to 17, x1 greater than or equal to 0, x2 greater than or equal to 0, and both x1 and x2 must be integers. The objective function is linear, and the feasible region is defined by linear inequalities. The only source of combinatorial difficulty is the integrality requirement. As in any branch and bound procedure, we begin by relaxing integrality. That means we now allow x1 and x2 to take continuous values. This relaxed problem is called P0. Solving P0 will give us, first, an upper bound on the optimal integer objective value, since this is a maximization problem. Second, information about whether branching is necessary. If the LP solution is already integer, we are done. If it is fractional, we will select a variable and begin branching. Now we proceed to solve P0. We now solve the LP relaxation, P0. The optimal solution of the relaxed problem is x1 equals 1.3, x2 equals 3.3. The objective value is z equals 14.08. This solution lies at the intersection of the two binding constraints. It is feasible for the relaxed linear program. However, it is not integer. Both x1 and x2 have fractional values. Since the solution violates integrality, it is not feasible for the original mixed integer problem. At this stage, we do not yet have an incumbent integer solution, but we do have something very important. The value 14.08 is an upper bound on the true integer optimum, because this is a maximization problem. The next step is to branch on one of the fractional variables. We now begin constructing the enumeration tree. The LP relaxation produced a fractional value for x1, specifically x1 equals 1.3. To enforce integrality, we branch on x1. Since x1 must be an integer, it can either be less than or equal to 1 or greater than or equal to 2. This creates two subproblems. The first subproblem adds the constraint x1 less than or equal to 1. The second subproblem adds the constraint x1 greater than or equal to 2. All original constraints remain in place. We now solve the LP relaxation for each of these two new subproblems. Each branch represents a smaller feasible region, and for each region, the LP relaxation will again provide a bound. We now evaluate both branches separately and compare their results. We now solve the LP relaxation for each branch. Start with the first branch, P1, where x1 less than or equal to 1. The optimal LP solution in this branch is x1 equals 1, x2 equals 3. The objective value is z equals 11.8. This solution is integer. So it is feasible for the original integer problem. That means we have found our first incumbent solution. The incumbent objective value is now 11.8. Now consider the second branch, P2, where x1 greater than or equal to 2. The optimal LP solution in this branch is x1 equals 2, x2 equals 0.5. The objective value is z equals 12.05. This objective value is higher than the incumbent, which is 11.8. So this branch is still promising. However, the solution is fractional because x2 equals 0.5. So P2 cannot be accepted as an integer solution. This means we must branch again, this time on x2. In branch P2, the LP solution is still fractional. We have x1 equals 2 and x2 equals 0.5. So we now branch on x2. Since x2 must be an integer, it can either be less than or equal to 0 or greater than or equal to 1. This creates two new subproblems. The first branch adds the constraint x2 less than or equal to 0. We call this a subproblem P3. The second branch adds the constraint x2 greater than or equal to 1. We call this a subproblem P4. At this point, we again solve the LP relaxation for each of these subproblems, and we compare the results to the incumbent, which is still z equals 11.8. We first solve subproblem P3, where x2 less than or equal to 0. The LP relaxation gives the solution x1 equals 2.125, x2 equals 0. The objective value is z equals 11.6875. Notice two important things. First, the solution is still fractional because x1 is not an integer. Second, and more importantly, the objective value 11.6875 is less than the incumbent value 11.8. Since this is a maximization problem, this means that even the best possible solution in this branch cannot improve upon the incumbent. Therefore, P3 is pruned by bound. There's no need to explore this branch further. Now consider subproblem P4, where x2 greater than or equal to 1. When solving the LP relaxation, we find that this subproblem is infeasible. There's no solution that satisfies all constraints together with x2 greater than or equal to 1. Therefore, P4 is pruned by infeasibility. At this point, all branches have either been explored or pruned. The incumbent solution remains x1 equals 1, x2 equals 3, with objective value z equals 11.8. Since no unexplored branch can produce a better solution, this solution is optimal. The branch and bound procedure has found the global optimum without enumerating all integer combinations. So far, we have seen how branch and bound systematically explores the solution space by splitting it into smaller regions. Cutting planes take a very different perspective. Instead of dividing the problem into subproblems, the cutting planes method keeps working with a single linear program and gradually strengthens it. We begin with the LP relaxation of the integer program. If that relaxed solution already satisfies integrality, then we are done. But most of the time, the optimal solution of the relaxation is fractional. When that happens, rather than branching, we add a new linear constraint, what we call a cut. This new constraint is designed to eliminate the current fractional solution, but it must satisfy one crucial property. It must not remove any feasible integer solution. Geometrically, you can think of this as slicing away a portion of the feasible region that contains no valid integer optimum. The feasible region becomes smaller, tighter, and closer to the true integer hull. After adding the cut, we resolve the LP. If the new solution is still fractional, we add another cut and repeat the process. One classical way of generating such constraints is through Gomery cuts. We will not go into the algebraic derivation of these cuts here. Instead, we focus on the intuition. Each cut removes fractional extreme points while preserving every feasible integer solution. In practice, pure cutting plane methods are rarely used alone. Branch and bound is typically stronger. However, when both ideas are combined, we obtain one of the most powerful frameworks in modern optimization: branch and cut. To make the idea more concrete, we return to the same integer linear program used in the branch and bound example. We maximize z equals 5.5 x1 plus 2.1 x2, subject to minus x1 plus x2 less than or equal to 2, 8x1 plus 2x2 less than or equal to 17, and x1 and x2 are non-negative integers. As before, we start by solving the LP relaxation, meaning we temporarily ignore the integrality requirement and treat x1 and x2 as continuous variables. The relaxed problem defines a convex feasible region in the plane. Inside this region, some points correspond to integer solutions, while others are fractional. The optimal solution of the LP relaxation typically lies at a corner of this polygon. If that corner happens to be fractional, which is usually the case, we then generate a cut that excludes this point from the feasible region. The important idea is that we do not change the objective function. We do not branch, We simply add a carefully constructed linear inequality that removes the current fractional optimum while keeping all integer feasible points intact. From here onward, the graphical illustrations will show how each added cut progressively shrinks the feasible region, guiding the LP solution closer and closer to the true integer optimum. We begin with the LP relaxation, denoted P0. When we solve this relaxed problem, the optimal solution we obtain is x1 equals 1.3, x2 equals 3.3, with objective value 14.08. From a purely linear programming perspective, this is perfectly valid. The point satisfies all linear constraints and lies at the vertex of the feasible region. However, it is not acceptable for the integer problem because both variables take fractional values. If you look at the figure, you can see that the feasible region contains many integer points, but also fractional ones. The LP optimum happens to lie at a fractional extreme point. The goal of cutting planes is to remove precisely this kind of solution. So instead of branching, we introduce a new linear constraint that excludes this fractional vertex. The key requirement is that this new inequality must still be satisfied by every feasible integer solution. In other words, we want to cut off the fractional optimum, but we must not eliminate any candidate integer optimum. Geometrically, we are shaving off a corner of the feasible region that contains no valid integer solution. After adding the first Gomari cut, labeled G1, the feasible region becomes smaller. You can see that a new boundary line appears and part of the previous feasible polygon is removed. The former LP optimum is now infeasible. We resolve the LP over this reduced region and a new optimal solution emerges. This solution is still fractional, but notice what has happened. The feasible region is now tighter. Importantly, none of the integer feasible points have disappeared. The cut was constructed so that all integer solutions remain valid. This illustrates the core principle of cutting planes. Each cut reduces the relaxation, eliminating fractional extreme points, while preserving the entire set of feasible integer solutions. Since the new LP solution is still fractional, we repeat the process. A second cut, labeled G2, is introduced. Again, this cut removes a portion of the feasible region that contains the current fractional optimum. The polygon shrinks further. The LP is resolved once more, and the optimal solution shifts again. At this stage, you can see that the feasible region is gradually being carved inward. The outer portions of the relaxation that allow fractional optima are being trimmed away. Yet all integer feasible points continue to satisfy the constraints. None of them are lost. Because the LP optimum is still fractional, a third cut labeled G3 is added. Now the feasible region is significantly tighter than the original relaxation. Visually, several fractional corners have been sliced off. When we resolve the LP again, the optimal solution moves closer to the integer lattice. The objective value decreases compared to the original relaxation, reflecting the fact that we are now solving over a smaller region. Finally, after adding another cut labeled G4, we solve the LP once more. This time, the optimal solution becomes x1 equals 1, x2 equals 3 with objective value 11.8. Now the solution is integer. At this point, no further cuts are required because the optimal solution of the LP relaxation coincides with a feasible integer solution. What has happened geometrically is quite powerful. By successively adding kits, we have transformed the original LP relaxation into a tighter polyhedron that approximates the convex hull of integer feasible points. Without branching, we have guided the LP optimum from a fractional extreme point to the true integer optimum. Of course, in practice, pure cutting plane methods alone are often not sufficient for large problems. But this geometric intuition explains why adding valid inequalities can dramatically strengthen a formulation. And this is precisely why modern solvers combine cutting planes with branch and bound and what is known as branch and cut. Now that we understand the theory behind MILP, let's see how this translates into practice using a Gurobi. At a high level, solving an optimization model in Gurobi follows a very structured workflow. The process begins by creating an environment, which manages licensing, logging, and solver configuration. In Python, this is typically done by initializing a Gurobi environment object. Next, we create a model inside that environment. The model is the container that will hold variables, constraints, and the objective function. Once the model exists, we define decision variables. For integer programming, this usually means specifying variables with type grb.integer or grb.binary. Each variable may also have bounds and optionally an objective coefficient. After defining variables, we add constraints. In practice, constraints are often added in batches using comprehensions or loops, which makes model construction concise and scalable. Then we define the objective function. In Python, this is typically done using quicksum to build linear expressions efficiently. Finally, we call the optimize method. At that point, Gurobi takes over and applies pre-solve, LP relaxation, cutting planes, branch and bound, heuristics, and many other internal techniques automatically. From a user perspective, the workflow is simple and sequential. Internally, however, a very sophisticated algorithmic engine is activated. A variable in Gurobi represents a single decision variable in the optimization model. Variables can be added individually using addVar or in collections using addVars. Each variable has several important attributes. The lower bound, referred to as LB, defines the smallest allowed value. The upper bound, referred to as UB, defines the largest allowed value. The objective coefficient, OBJ, contributes directly to the objective function. The variable type, vtype, determines whether the variable is continuous, integer, or binary. For integer programming, vtype is typically set to grb.integer or grb.binary. After optimization, additional attributes become available. For example, the attribute x contains the value of the variable in the optimal solution. Gurobi allows both positional arguments and named arguments when defining variables. For clarity and robustness, named arguments are usually preferred in practice. Variables can also be defined as multidimensional arrays or indexed by tuples. This is extremely useful in industrial models where decisions are naturally indexed by time periods, locations, products, or other dimensions. In short, variable definition is flexible, expressive, and designed to scale. To illustrate the modeling process, we consider the following integer linear program. We maximize, so equals 2, x1 plus 5, x2, subject to x1 plus 2, x2 less than or equal to 25, 2x1 minus 4, x2 less than or equal to 8, minus 2x1 plus x2 less than or equal to minus 5, and both variables are non-negative integers. This example is simple enough to visualize graphically, yet rich enough to illustrate integer programming behavior. We will now translate this mathematical formulation into Gurobi code and observe how the solver processes it. We begin by importing the Gurobi library. Then we create a model object. This model object will contain everything: variables, constraints, and objective function. At this stage, no optimization has been performed. We have simply created an empty container. In parallel, the figure on the right shows the coordinate system in which we will visualize the feasible region. Initially, no constraints or variables have been defined graphically. This separation between model construction and optimization is important. We first build the mathematical structure, and only then do we ask the solver to process it. Next, we declare the decision variables. Both x1 and x2 are added as integer variables with lower bound 0. At this point, the feasible region consists of all integer lattice points in the first quadrant. Graphically, you can see the integer grid appearing in the non-negative region. No constraints have yet been enforced, so all integer points with non-negative coordinates are currently feasible. This step highlights an important modeling concept. Integrality is enforced directly at the variable level. We now add the three linear constraints to the model. First, x1 plus 2, x2 less than or equal to 25. Second, 2, x1 minus 4, x2 less than or equal to 8. Third, minus 2, x1 plus x2 less than or equal to minus 5. Each constraint restricts the feasible region by introducing a linear boundary. Graphically, the intersection of these half spaces defines a polygonal feasible region. Only integer points inside this polygon are feasible solutions to the integer program. Notice how the feasible set is now the intersection of the lattice and the polyhedron defined by the constraints. This intersection is exactly what makes MILP problems challenging. After variables and constraints are defined, we specify the objective function. We set the objective to maximize 2, x1 plus 5, x2. Then we call the optimize method. At this moment, Gurobi performs pre-solve reductions, builds the LP relaxation, generates cuts, applies heuristics, and executes branch and bound, actually branch and cut, internally. From the user's perspective, it is a single command. From the solver's perspective, it is a complex orchestration of advanced algorithms. In the figure, the optimal solution is highlighted. It corresponds to the best feasible integer point in the polyhedron. Finally, we examine the solver output. The log shows model statistics such as number of rows, number of columns, and number of non-zero coefficients. It reports pre-solve reductions, root relaxation results, and branch and bound progress. You can see the root relaxation objective value, node exploration statistics, and incumbent improvements. At the end, Gurobi declares that the optimal solution has been found with a zero optimality gap. For practitioners, understanding this log is important. It provides insight into model difficulty, relaxation strength, and search efficiency. Even though the user wrote only a few lines of code, the solver internally executed a sophisticated algorithmic pipeline. Up to this point, we have seen how mixed integer linear programming models are constructed, how binary variables capture discrete decisions, and how constraints translate business rules into algebra. We have also discussed solution methods and how solvers explore the feasible region to find optimal integer solutions. Now it is time to move from theory to practice and actually build and solve a model ourselves. For this reason, this section is designed as a hands-on exercise. Along with these slides, you will find a Jupyter notebook that accompanies this exercise. You should open it now because from this point on, the goal is not just to understand the formulation, but to implement it in Gurobi and solve it computationally. We will first describe the problem and formulate it mathematically here in the slides. Then, in the notebook, you will translate that formulation into code. So let's begin. We consider a consulting company that has three open positions: software tester, software developer, and solutions architect. There are three candidates: Alex, Bob, and Claire. Each candidate has taken 3 competency tests, 1 for each position. The result is matching a score between 0 and 100. A higher score means a better fit between the candidate and the job. The table summarizes these scores. For example, Bob scores 80 for software tester, 47 for software developer, and 67 for solutions architect. Our goal is to assign candidates to jobs in a way that maximizes the total matching a score. However, we must respect 2 rules. First, only 1 candidate can be assigned to each job. Second, each candidate can be assigned to at most 1 job. So the core question is simple: how do we pair candidates and jobs so that the overall compatibility score is as large as possible? This is a classical assignment problem, and it is a perfect starting point for binary modeling. To model this problem, we first define the decision variables. For each candidate I and each job j, we introduce a binary variable x, I, j. This variable equals 1 if candidate I is assigned to job j, and 0 otherwise. So the model does not directly choose names. It chooses binary assignment decisions. Now let's translate the business rules into constraints. First, each job must be assigned exactly one candidate. That means that if we sum xij over all candidates for a fixed job j, the result must equal 1. Second, each candidate can be assigned to at most one job. So if we sum xij over all jobs for a fixed candidate I, that sum must be less than or equal to 1. Finally, the objective is to maximize the total matching a score. For each possible assignment, we multiply the score MSIJ by the decision variable xij. Then we sum over all candidates and jobs. The solver will choose the assignment pattern that maximizes this total score. At this point, the formulation is complete. Your task in the notebook will be to translate this structure into Gurobi code. Now, we extend the same scenario, but introduce a realistic complication. There's a budget constraint. The total budget available is $5,000. Each candidate has a fixed cost, independent of the job assigned. Alex costs $1,000, Bob costs $2,000, and Claire costs $3,000. Now the assignment must respect not only compatibility, but also budget feasibility. Because of the budget limit, it may no longer be possible to fill all 3 positions. This changes the structure of the problem. We must now allow the possibility that a job remains unfilled. This is an important modeling insight. Sometimes constraints force us to modify the decision structure itself. We keep the same assignment variables xij as before, but now we introduce an additional binary variable gj for each job. The variable gj equals 1 if job j is not filled and 0 otherwise. The job assignment constraint now changes slightly. Instead of forcing exactly one candidate per job, we write that the sum over candidates of xij plus gj equals 1. So either the job is filled by exactly one candidate, or it is marked as unfilled. The candidate constraint remains the same. Each candidate can take at most one job. Next, we add the budget constraint. We multiply each candidate's cost by the corresponding assignment variable and sum over all candidates and jobs. That total must be less than or equal to the available budget B. Finally, we modify the objective function. We still maximize total matching score, but now we subtract a penalty term. Specifically, we subtract M times the sum of Gj. This big M term penalizes leaving a job unfilled. The penalty should be large enough to discourage unnecessary gaps, but not so large that it distorts numerical stability. So the solver now balances 3 forces. A, maximizing compatibility. B, respecting the budget. And C, minimizing unfilled jobs. In the notebook, you will implement this extended model and observe how the optimal solution changes compared to the fully funded case. Before we conclude, I have included a small set of references on this slide for those of you who would like to explore the material in more depth. They cover both the theoretical foundations of linear and integer programming, as well as practical resources for implementation and experimentation. You may find them useful as you continue working with optimization models beyond this course. Let me now briefly sum up. Throughout this course, we have moved from the basics of linear programming to the introduction of integrality, modeling techniques, and the internal mechanisms of modern MILP solvers. We have seen how discrete decisions fundamentally change the structure of an optimization problem. We have discussed how LP relaxations guide the search for integer solutions, and how methods such as branch and bound and cutting planes operate behind the scenes. Most importantly, we have practiced translating real decision problems into precise mathematical formulations and implementing them computationally. If there's one skill to retain from this course, it is the ability to model clearly. Algorithms are powerful, solvers are sophisticated, but the quality of the solution ultimately depends on the clarity and correctness of the model. Integer programming is a mature and highly developed field, yet it remains extremely relevant, both in research and in industry. The tools you have seen here are used daily in large-scale planning systems, supply chains, transportation networks, and many other domains. I hope this course has given you a solid foundation, both conceptually and practically. and that you now feel comfortable reading, formulating, and implementing MILP models. Thank you for your time and engagement.